The goal of this video is to give the viewer some more insights into some further problems in optimization. We've got two examples in this video. The first one, hostel manager agrees to accommodate a party of students for $70 per student if the party is 50 students big. He also agrees to reduce the tariff, that's the cost, by $1 per student for each student in excess of 50, so if it's over 50 in number, up to the capacity of the hotel, which is 75. Find the size of the party which will maximise the revenue for the hostel owner. So we need to look at the information and clarify that first. We can predict that this is going to be an optimization problem where we've got to find a maximum. And we need to clarify some terms, especially revenue. Revenue is basically the gross intake of money, as in it's the gross earnings, basically ignoring costs or fees, so we're not considering those things, just the money coming in basically. So I'm going to let R be the revenue, and we need to find R versus the number of students, okay, which I'm going to make X. So we've got R is proportional to X in some way. In general, R is the number of students times by the tariff. So let's see if we can turn that into an equation now, and also look at any restrictions on the domain. So we need to look at our domain. It's got to be at least 50 if we look at the wording. So, and there won't be any profit unless X is actually over 50, and of course the hostel capacity is 75. So really we've got 50 is less than X, which is less than or equal to 75. It's arguable about whether it's less than or equal to. You see, 50 is acceptable, but you don't get that that tariff kick in. So I guess 50 works, but you know the profit's going to be lower probably. So we need to work out the number of students in excess of 50. So in other words, an expression. So we'll have X minus 50 is the number of students in excess of 50. The tariff per student is the $70 standard amount minus the number of students in excess of 50. So you can see that that's carried down there. So that is carried down to there. You could actually write multiplied by 1. Okay, so it's $1 for every X minus 50 we have. So for every student over the number 50, we take $1 off. So we're just translating the text in English into mathematical expressions and equations. So let's simplify that. That would be 120 minus X, provided X is above 50. So we can look at our proper equation now for revenue. So it's the number of students, which is X, times the tariff per student, which is simplified to 120 minus X. If we like, we can expand that out, so that would be 120x minus x squared. We have a stationary point at x equals 60. We do what we normally do. We take the derivative, look for the stationary points. Okay, we need to check whether that is a min or a max, because we're after a maximum profit, or I should say maximum revenue. So there's something we can do what we normally do. We can look at the gradient before, at and after. There is another way of checking for max or min. We use a second derivative test. So here's another option. We can do before, at, after to see if it's a max, min, or even an inflection. But there's a second derivative method of doing it. So if we take the second derivative, which is the derivative of the derivative, so you write that as d squared r over dx squared. And the reason why that is what it is, because you've got d dx of dr dx and so what we do is the notation we use is d. See how there's a d there and a d there? That's a d squared is the notation. R over, there's two dx's on the bottom, so that's dx all squared. That's how the notation works. So we take the derivative of 120 minus 2x, okay, and that would be negative 2. Now that means that we can determine whether it's a max or a min. If it's negative, that means that the rate of change of the gradient is reducing. So that means the gradient is getting smaller and smaller and smaller, which is what happens at a maximum. If it were positive, so that's if it's negative, if it were positive, the gradient is increasing. The gradient is changing and it's increasing in that area, in that interval. So that's if it's positive. So that's the second derivative test. You're welcome to continue using what we've been using, but that proves that it's a maximum. Okay, so it's one of these scenarios here. If it were positive, it would have been a minimum, and that's not how to maximize revenue. Now, in optimization problems, we need to check our solution, of course, against the max here, the stationary point, but we also need to look at the endpoints, because that maximum could have been, is it a global or a local maximum? Because if it is only local, the endpoints can be higher. So that's why we do that local or global. If it's global, it dominates the whole function across that interval of interest, but if it's only local, the endpoints may be higher. So we substitute that into the equation for r of x. So we go r of 60, we need to test r of 50, we need to test r of 75, and to save time I've already calculated those, so I'll put them up. But by doing those substitutions, we do see that the best outcome is the maximum. So the endpoints are lower, so you get $3,600, and you would check that with your verify it with your graphics calculator and use electronic methods to verify that. Let's look at the second question. Okay, so this one here, we're going to go through it fairly quickly. It is a more complex one, so you may need to use pause and rewind. So we've got a window in the form of a rectangle, and it's been what's called surmounted by a semicircle. So that window there, it's got a rectangular part and it's got a semicircle on the top there. And we've got to find the maximum area of the window if the glazier has a 6 meter length of seal, which is to be placed around, so i.e. it forms the perimeter, and we're going to assume that, you know, we don't have any left over, we've got enough, there's the complications aren't there. Okay, so we need to work out how much seal goes around, well, not how much seal, we've got 6 meters, and how big can we make the area and stick to the 6. So you can see in the diagram there that we've got R for the radius of the semicircle, and we've got L for the length of the rectangular part of the window. So they're givens, and use those. So the perimeter would be 2R plus 2L plus pi R, because that's half of a circumference, and that's equal to 6. So to get 2L, we can rearrange and then divide through by 2, and we've got a function of L versus R, which is going to be handy here. So we have L versus R, the function L of R. Using decimal approximations, we've basically got that relationship. So area is the area of the rectangle and the area of the semicircle. So we write an expression down for that. That's A of R. Okay, and simplifying, we get this here. Now we take the derivative of that because we want a relationship between the area and the radius, because once we work out a maximum R value to make the area a maximum, we can then go back to this relationship here and find out L correspondingly. So we take the derivative and R equals 0.84 once we set the derivative there equal to 0. You can, as I said in the previous example, you can use a second derivative test, or you can look at the nature of the gradient before, at and after the stationary point to determine whether it's a max or a min. Using the second derivative, it's a negative, so it is a maximum. So we have a maximum with that corresponding R value. Now we can substitute that in to find an area, and the area is 3.48. And if we want to know what the corresponding length is, not that the question asks us for that, but we can go back to this here to find out the length if that's important. It hasn't actually asked us for that, so I'm not going to do that in this video. And of course you get your graphics calculator.